right, there we go. Hi, everyone. Thanks for staying. Hi. Thanks for hanging around for the last talk, Blasting Past Webp. My name's Ian Beer. I'm the tech lead of Google Project Zero. I mostly do vulnerability research. I presented here last year on XNU kernel exploitation. And I think I mentioned then that over the last few years, I found more and more of my time is taken up analyzing in the wild iOS exploits, to the point where I've been doing it now pretty much non-stop for the last 18 months. Just the constant flood of stuff that's getting caught in the wild. There is more than I can possibly analyze. So before we get started, a few quick shout-outs. Thanks to Google Tag, who, since I made this slide, are no longer called Google Tag, as well as Amnesty International's Tech Lab and iVerify. Without their assistance, none of this would be possible. So what are we talking about? Today, I'm presenting on Blastpass. So this was September 7th last year. Citizen Lab published this blog post. NSO group, iPhone zero-click, zero-day exploit captured in the wild. And they referred to the exploit chain as Blastpass. Capable of compromising iPhones running, at the time, the latest version of iOS, iOS 16.6, without any interaction from the victim. This exploit involved passkit attachments containing malicious images sent from an attacker iMessage account to the victim. So at the same time, Citizen Lab published this, Apple published an advisory with not much in the way of detail, but still enough juicy, exciting things for people to try to follow up on. A buffer overflow issue addressed with improved memory handling, and a validation issue with improved logic. So very soon after this, a couple of folk published their analysis of what actually the underlying vulnerability was. I am not going to dig too much into that. If you're really keen on understanding the intricacies of why there is a bug here, go read Ben Hawkes' blog post here. Sadly, he missed the trick by not making that very cool, trippy image a Webp. Sadly, it is just a PNG file. And then early November, out of absolutely nowhere, this blog post appeared. It's the first blog post ever on this blog. This group called Dark Navy, who built on that work to demonstrate how you can actually exploit this vulnerability here in the context of Chrome. So they use the corruption primitive that we'll look at to target a reference count of a CSS object in Chrome. And then because they have JavaScript code execution, they are able to manipulate the environment as things move along to kick things off. What I was super interested in, though, was how do you exploit this without that? What are the tricks involved in turning this around? To give a bit of a timeline, it was around about this time, so a month or so, or no, 2 months or so later, that I was able to get a sample of the Blastpass exploit. So unlike forced entry, that I, along with many other collaborators, analyzed a few years ago, I had no expectation of actually getting this sample, which fundamentally meant I had no actual test devices running the correct targeted version of the exploit sample that we had. And also, 2 weeks after this, I took 3 months of paternity leave, kind of with my fingers crossed that someone else would take up this challenge and do the exploit analysis for me. But returning in March of this year, no one had. And with 2 months to go until OffensiveCon, the clock was ticking. And yesterday, someone here at the conference actually gave me a vulnerable device. So this is what it looks like when, with this person's vulnerable device, you try to exploit someone with Blastpass. So we just have a script there in the bottom corner that's generating and signing a bunch of these PKPass files. You highlight them, you drag them, and you drop them into the iMessage window, and you press send. And what you get it's unclear unless you spent many, many months actually staring at this, but this exploit actually worked. This only failed because of the ASLR bypass not working. Remember this hex constant, and depending on how quickly I can talk, it may become clear, or you can hang around for an extra half an hour at the end. So I'm now going to put on my computer science hat, and we're going to smash as quickly as possible through how you get the kind of interesting and very restricted primitive that this bug gives you. So Webp, specifically the lossless format, the lossless subset of the Webp format, uses Huffman trees. Here is a Huffman tree. A Huffman tree is a prefix code tree. You go left or right down this thing. You have here very arbitrary symbols. In Webp, there are, lossless Webp, there are 10 different Huffman trees. We are interested in 5 of those Huffman trees, and the symbol values that you will use, you can think of as the color intensity values for each of the channels, plus some extra channel. So here's a Huffman tree. You may have looked at these things in university before, or just in capture the flag. So you will traverse down. So for A, we would have this prefix code of 0, 0, D, 0, 1. You can look at it like this. Now, Huffman tree is a very space-efficient but slow data structure to traverse. You don't actually want to have to like follow pointer chains down to here. So any actual usage of Huffman trees makes a trade-off where they use much more space, but for a much faster lookup. And so I will try in 30 seconds to explain what that trick is. You take the codes that you see here, read bit by bit from left to right, look at the length of them, and then you reverse the codes. So now you read them from right to left. Now, you take all those codes, and you left pad them with zeros. And now, in your brain, you say, OK, those codes are now indexes into an array where we now fill this array in with all of those symbols. So we take the symbol A, which we see, well, anything where we consume a 0 and then a 0 corresponds to the symbol A, which has a length 2. So we take this first entry, and then we skip forwards by 4, and we skip forwards by 4, and we skip forwards by 4. And we do a similar thing for D. We skip, 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 E, skip, skip, skip. And then we come on to a slightly longer code, C, and now we skip slightly further. The important thing here is this is why there is this skipping primitive which the vulnerability uses, and is often something that's very helpful for heap exploitation in the presence of some kind of mitigation or cookie or other things like this. Primitives that are not just a linear overwrite, but are skipping ahead can often be very valuable, even if what you get to write, as you will soon see, is exceptionally restricted. So you fill in the final 2 entries here of B and F. Now, this is a very simplified Huffman table. The size of this table obviously grows exponentially with the number of bits. And so if you have, as you do in this case, codes which can be 20, 23, 24, 25 bits in length, well, you don't want a table that's 2 to the 25. So you actually have some kind of paging style indirection where you can have 2-level page tables. And go read Ben Hawkes' blog post if you want to understand what bit of the maths they got wrong calculating the size of these extended tables. But in the end, what you end up with in memory is an array of Huffman lookup table entries, which actually look like this structure here, corresponding to this diagram, where we have the number of bits here as a single byte and a value as 2 bytes. So the value here being A, this arbitrary symbol, and the bits being 2. And then if you try to run the POC under address sanitizer, you will see a crash in replicate value, which, as the comment in the Webp code tells you, that it's doing this skipping. Although in reality, despite what that comment might make you think, it actually fills it in backwards, but that's irrelevant for us. And yeah, it's slightly more complicated. So the TLDR of the primitive that you have to exploit remotely in a 0-click, 0-interaction setup is there will be a hex 3,000 byte allocation of these Huffman tables. And the primitive you get is that hex 58 bytes off of the end of that, there will be one single Huffman code value written with these two fields. And you think, oh, well, you surely have quite a bit of control over this. Well, it actually turns out that the way the overflow works, you can only do it with the very last Huffman table, which has a much smaller symbol set than the earlier tables. So you can actually only have values from 0 to 39. And you're going to need to use a lot of bits in order to trigger the bug to make these tables too big. So there is a tiny, tiny bit of leeway in what you can do. But this byte here is definitely going to be 0. This is definitely going to be 0. This is going to be 7 or lower. And this is going to be something fairly close to 27. So yeah, there's not a lot of scope here. So what would you do? And now I'm kind of looking in the audience for the people who know what they would do. Because one thing I will also point out is that there are still some gaps in the analysis of this. And we will discuss those as we go along. So, I mean, my initial approach to looking at this was write a Webp parser. I have the Webp thing. And this is what I did when we also analyzed the forced entry JBig2 payload. And I remember before we figured out how they were using weird JBig2 transforms, I remember just reading through the spec and implementing the parser and being like, this is amazing. Why do they have this? And indeed, Webp continues to deliver. So the transforms are reversible manipulations of the image data that can reduce the remaining symbolic entropy by modeling spatial and color correlations. They can make the final compression more dense. And Webp has a bunch of these transforms. And indeed, like the spec has all of this pseudocode. Now, before you get too excited, Ben Hawkes, in his analysis, did already point out that whilst you can trigger the bug with a malformed Webp, he could find no way to bypass a consistency check that happens after the memory corruption, where it can effectively tell something went wrong in the construction of this Huffman, in the construction of these Huffman tables. Like the number of nodes does not match the expectation for a valid canonical Huffman tree, and it bails out. And that is the case. This bug does not bypass this bailing out, which in many ways makes the exploit even more fascinating, that in order to trigger it, as soon as it's triggered, it returns an error code and parsing stops. So the next step is to then take a closer look at what is actually inside the Webp, which is inside these pkparse files. The first thing you notice is quite big. It's very big for a 20 by 20 pixel image. And so if you write a Webp parser and you start walking through all the different things, you see the size is about 5 megabytes. But the actual lossless segment of the file is only about 1K. And you can see here, this is the first of the 10, starting to parse the first of the 10 Huffman tables that are involved here. So the next obvious question is, well, what is the rest of it? If this is really just the trigger, and it is, there is nothing else apart from trigger the bug. Well, the next thing directly after there is an EXIF. And this EXIF, unlike the very tiny lossless thing, is absolutely enormous. It's a 5 megabyte EXIF, which has effectively inside a sub directory 1 entry. Now I'm looking for people who know what that tag is. There are a handful of mentions of it on the internet in 2 contexts. One is people from the photography community trying to figure out how to parse. There's a page that I didn't put on here where someone's like some forum post like, how do I parse this gibberish? What is this? And there are some other posts from other places who do know how to parse this gibberish. So there are tons and tons and tons of EXIF tags out there. It's actually pretty overwhelming. 927C, make a note. Manufacturer-specific information. It's pretty damn vague. But Wikipedia has our back. And it has those 3 beautiful little words that every vulnerability researcher wants to hear. The make a note tag contains image information, normally in a proprietary binary format. If we had a bit more time, I would now spend like 5 minutes doing bingo about what people think the proprietary binary format that Apple chose to put support for in every single image that your iPhone parses, which it will do to any of you without you even knowing. But we'll just skip the bingo. It's obviously a plist. It's which I think is bad enough. They could have, to their credit, they could have made even worse choices, but sure. This is still pretty bad. Well, not only is this a plist, this is a really, really massive plist. So I have a bunch of tooling. This is not my tool, sadly. This is Apple's tool. For parsing plists, they did not work. This plist is too big, and I had to refactor all of my code. But just extracting the bytes of the binary plist out and loading them directly in a test thing, and just throwing it in instruments, not to analyze the heap groom, but just to like get a vague idea of what's going on. You can see this thing is really, really big. So all I'm doing here is loading the binary plist. It's making almost 500,000 allocations, manipulating almost a gigabyte of memory. And actually, one of the things that I encountered quite frequently when trying to reproduce this is that you get memory pressure failures inside Blastpass. Because this spikes and drops down pretty quick, but the spike is pretty impressive. And if you look a bit more closely, there are some very, very suspiciously round numbers inside here. Like, it is no coincidence that that is exactly 20,000, or that there are exactly 20,000 transient NS dictionaries inside here. And 2 of the other things that are particularly interesting, there are 2 sets of very large allocations, 1 and 4 megabyte ones, and we will look more closely at those in just a second. So I did refactor my plist parsing code, because my preferred approach for analyzing these things is to try as much as possible to start sort of from looking at the code, seeing what it does, and trying to figure out the primitives that the exploit author is trying to build. So what is the primitive here? This is inside a dictionary, inside a plist. It's got a key, swxj, and it maps to a string of A's. And then it's got the matching key, which also was not supported by my earlier plist parser. It took me a while to realize that I had a bug in my plist parser, that I couldn't see the heap groom, because the heap groom this is effectively how it's operating, right? Using key collisions to cause allocations and freeze. But not just 1 or 2 key collisions. So then they have another dictionary with the value mapping to a dictionary, which maps to a dictionary with the same key with 1 entry, which maps to a dictionary with the same key with 2 entries with the same key. And this goes on and on and on and on, 80,000 times, all the way down here. And I was like, nah, I don't think my approach of just staring at this is actually going to scale to this point. So let's take another approach. There are a handful of much bigger allocations. These are string and data objects which are inside there. The numbers on the left become way more interesting and suspicious looking when you look at them on the right, in that these are very near to allocation bucket sizes for the allocator that we're about to look at. Almost all of these don't have anything very interesting in. They either are just A's or just have a single bit set in different places. All of them, that is, apart from that one, which is very interesting indeed. This is another one where I want to look at the audience. You know how long I stared at this thing for, and people in my office can confirm. But I know that some people in this audience can look at that, and they see an object, and they know what type of object it is. Who does? Because I can't unsee it now, but yeah, it is not clear at all. Some things immediately stand out, however, right? you can see my cursor very well. I can go and sound. Oh no, I can't. I don't know if you can see my cursor. But I mean, that's a pointer, right? That's a pointer that is actually, all of these pointers are clearly into the shared cache, which already tells you that, yeah, we don't necessarily have absolutely every part of this, because this is not something that's being dynamically generated, right? This is just packed inside that Webp file. But these are pointers. This is a length, and it is a length. And if I speak fast enough, you'll see how it's a length. But the real question, the question here is, what is this object? Like, how is this used to do something useful? So whilst I was analyzing this, I was also trying to just render these things in a way that would emulate what's happening inside the Blastdoor sandbox. And just looking around in LLDB. And so this is an LDB session right after the Huffman table, which is the buffer that's going to be overflown out of, has been allocated. And as I said, that thing is hex 3,000 bytes. And this is what you see at that address. What's suspicious here? Like, that is a suspiciously round number. And it's not just because this is like a fresh session or something. This has already parsed the binary plist. By round number, I mean the address here that is 3,000 plus that. And if you do it again, you're like, ah, that's weird. It's like it's, again, add 3,000, which is the size of the buffer. It's 8 megabyte aligned. Like, that is too much of a weird coincidence. And so I think there was already a talk earlier about user space malloc. So we're going to go a quick 45-second refresher on user space malloc. Specifically, this is the libmalloc small region, which allocates 8 megabytes in chunks of 8 megabytes. For our purposes, we'll think of it as having 3 different little regions. There's a hex 28 byte header, then there's some metadata, and then hex 8,200 bytes after the start. We start splitting it into these 512 byte chunks, which are pointers to those are what's going to be given back to user space. So if you've ever doing some stuff in Xcode, and you probably noticed this like hex 8,200 coming back in early malloc allocations. Well, that's why, because they start from the beginning there. And so for each of these 512 byte chunks, you have an associated 2 bytes metadata word, which itself is then split into a free flag bit and 15 count bits. And so for each chunk, you get a metadata word like this. And this splits up into 16,319 512 byte chunks. And then obviously these regions, depending on allocation patterns, these can be together or far apart, or there can be other regions or other kinds of things. But there is no guard page between these. And so the behavior that we just observed rendering the image was that the Huffman table, hex 3,000 byte allocation, pushed right up against the very end of this, such that that hopping primitive hops over into this metadata word, not corrupting all of the stuff in the middle here. So let's look at a runtime sample of the groom working partially when we render the Webp, having loaded the EXIF metadata. So again, this is the corruption with this 32-bit value. What's going to happen is a 7 is going to be written at the end of this in-use chunk. This number here, 19 at the start, I didn't explain, but this is the count of, in this case, if the free bit is clear, this is saying, here is this maps to the start of allocation, which is 0x19 times 512 bytes in size. So that's how the allocator can go from the pointer back to figure out, well, how much of this memory do I free when I free it? So it corrupts this size with 7 and this with 27. which in some cases is invalid, and in some cases is valid, depending on the exact allocation and free pattern and when it gets freed and a bunch of other things. Some types of metadata corruption are detectable and are detected sometimes under certain circumstances, but with the correct vulnerable version, it is not detected. And to make it even clearer that this is no coincidence whatsoever, whilst we have had that Huffman table pushed right up against the end of the 8 megabyte region, then it just so happens that when you hop hex 58 bytes past there, the metadata word that is right here happens to be code lengths, or that correspond to the allocation of code lengths, which is the very next thing that gets freed. So when I say that the Huffman table corruption, when that occurs, the system knows that something has gone wrong and it bails out of the Webp parsing, frees everything. That's the very next thing that gets freed. Again, indicating that this heap group, this very, 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 very big binary plist was setting things up such that these things lined up perfectly to turn what was a corruption with this into some overlapping allocation or use after free primitive. The question is, what? What is the next step? Especially because the very next thing that's going to happen is Webp parsing fails and everything gets cleaned up. Or at least that would be the case. I've got to start speaking faster. That would be the case if this were just a Webp. But this is not just a Webp. This is a Webp inside a PK parse file, which, by the way, is just a zip file with a manifest and a JSON file. And so if you actually run file, which I'm embarrassed to say I actually didn't do for at least 2 months, because everyone is talking about the awesome Webp exploit, this logo.png, it's not a PNG. Well, it turns out background.png is also not a PNG. It's a Tiff. And again, that is no coincidence. But that still doesn't answer the question of, well, why? What is it doing? So of course, what do? You write a Tiff parser. And when you write the Tiff parser, you see this Tiff contains one compressed strip. And when you decompress the strip, this is the image. This is the image before the alpha channel values have been rendered. This is what you get. And if you remember back to when I asked whether people knew what that strange-looking object was, well, there are many similarities with this object. What is this? Because it's definitely not a Tiff image that you want to look at. Although it does actually render, unlike the Webp, you can look at this. Right, so this is then back to that mysterious 1 megabyte heap group. And you can see there is definitely some similarity here with like a 0 keyword, then like 13, 84, 13, and then a 1. You see here there's like a 0 keyword, then an 80, 26, 1. But I could not figure out what this was. And again, there are people here who are thinking that I'm an absolute idiot for not knowing. Not many people. There are like 2 or 3 who are like, it's obvious what that is. It's definitely not. So the way I figured it out was I just kept I kept taking core dumps of some app and then grepping through the memory, effectively looking for similar looking patterns until I found one where it's like, this is again too similar to be a coincidence, except it's slightly different. And I do recognize what this thing is at the start of this. This is looks to me like a non-pointer ISA, right? So it has the least significant bit of a pointer set, which is already like a strong signal that this is some Objective-C thing, and also some kind of tag bit set up high. But anyway, if you just remove those 2 So remove the least significant bit and clear this high bit. And in LDB, look up the thing, and I'm like, oh, this is an NSCF array. Kind of interesting. And that is the trick you need to be like, these are core foundation objects. And core foundation, Apple haven't released the source code for core foundation for a long, long time. But fortunately, the code from like 20 years ago is still pretty accurate. And it is indeed telling you, this is not 20 years old because it has support for 64-bit, but it's still about 8 years old at least. And it's telling you that, well, we have this CF info thing inside these core foundation objects. And we'll just skip ahead, and you can see that this 13 corresponds to CF array get type ID. This is telling the core foundation runtime, this is a core foundation array. And similarly, this is telling the core foundation runtime that this thing is a CF read stream. And sort of, there are a few interesting things here that I have not spoken fast enough to cover, but I'm just going to keep going until someone throws me off the stage. That whilst typically you would expect every Objective-C object, and indeed every toll-free bridged object that's coming between like the C world and the Objective-C world, to have an ISA pointer here, as long as you're calling a certain subset of core foundation operations, this ISA is totally optional. Like, it can be null, and indeed it is null in this case. So there is a missing step that with the phone that someone lent me at this conference, I'm trying to figure out as to what it is that core foundation array inside the Tiff somehow leads to CF release getting called on this thing, which I now know to be a CF read stream object. And so we can very, very quickly then look at, once a CF release gets called on this, well, doesn't pack mean that it's all over? And the answer is, well, in the case of a regular kind of JOP exploitation, where we imagine that, in this case, x8 points to controlled data, then we'd read a packed function pointer here, and you would need some kind of either ability to copy a zero context function pointer from somewhere and put it there, or some signing oracle or something like that. There is a bypass which is relatively well known and certainly has been documented before, where, well, as long as you can find pointers to the packed pointers that you want to use, you can just chain these together, and this is absolutely enough. So they're effectively using this kind of callback chaining, where rather than the gadgets being a function that I want to call with, for example, the wrong arguments, it's instead the gadget set is restricted down to not only entire functions that you want to call, but functions to which there is a signed pointer at a known address in the shared cache. And it just so happens that this is extremely common because Core Foundation, for example, is basically built on the notion of you define the semantics of your objects with these arrays of callback function pointers, which, because of pack, all get signed and put at fixed locations in the shared cache. We'll just smash straight through this. You all know how JOP works. It's just one level abstracted above that, because there is one last mystery, which is, but wait, what? You can't just put pointers inside the image. And indeed, this is why something is missing, and it's completely unclear whether it is even fixed. It is very evident that there is some other memory disclosure, ASLR, bypass that's being used to bootstrap this. Unlike forced entry, which was you send a single image and everything happens inside this weird machine, that is not the case here. And so iVerify shared, this is from their blog, this image of, from a real target, this sequence of, again, very suspicious looking crash logs, where you have a bunch of home D crashes, followed by a bunch of Blastdoor crashes. And looking at these, all the Blastdoor crashes, they're not attempts to trigger the bug. They're like crasher issues, just trivial stack overflows, right? So recursion walking off the bottom of the stack and hitting the guard page. But the HomeD crashes, they are not like that at all. They look way more suspicious. And I did look through the Apple bulletins to try and find fixes in HomeD that were like around about the time that the Webp bug was fixed, and there are none. So this has also been that particular aspect has also been covered by Citizen Lab. They have other forensic evidence pointing to what looks to me like a different HomeKit issue that was clearly then also connected together with some other Blastdoor issue that was indeed also using the make a note technique to presumably do a similar, if not the same, heap grooming. So hopefully, sometime in the time frame of the next week to the next 6 months, I will finish a blog post where all of the intermediate steps are laid out in way more detail. The idea here is to give you like a taste of how it's possible that this thing can work. And indeed, one of the key takeaways for me is heap metadata corruption in 2023. It's kind of surprising that it works, or maybe it's not. The second takeaway would be that it's clear that there's a separate memory disclosure. And it's not necessarily that it made exploitation simpler. This is not necessarily a simple exploit. It appears to be a very well-executed version of fairly known techniques. There's no JBig2 style, completely custom new weird machine here. Yeah, there are still some gaps that I don't understand. And this seems to be like a fairly universal pack plus JOP technique that, short of data pack everywhere, I don't see an obvious way to get around or for it to be mitigated. And so with that, and the clock stopped a while ago, thank you for your attention, and any questions? I will also be at the party, so we can save the questions for later.
Do you have any sense of the tools with which this was debugged?
This is a very good question.
Was this constraint so?
Right. So the question was like.
It continues.
Yeah. The question was like, what kind of tools were used to build and debug this? The parallel question being, why don't I have whatever tools were used to debug this? Because it's clear that like debugging, surely, hopefully, is necessary. So I think there's a spectrum of tools that people use, right? One side of it is teams will have some form of private jailbreak that gives them the ability to at least inspect into the bits of the system that they want. I went down many, many rabbit holes trying to analyze this. Like I wrote a custom debugger using hardware breakpoints to try and like figure stuff out. Wait for the blog post. The other question, though, I guess, is about like the level of custom tooling that is being developed to build these payloads. So Matthias from iVerify gave a talk looking at a latter part of this chain where they have an NS expression-based payload that actually does kind of kicks off the next stage, trying to like pull down their sandbox escape exploit. And those kind of payloads, definitely people are writing custom compilers for like their own custom intermediate language that they lift into this weird machine. As to the tooling for the heap manipulation, it's hard to know because I don't know how the heap manipulation works yet. I just scroll through it and I'm just completely overwhelmed. So for me, it's like I've got to build the tooling to understand it, to then be able to understand the tooling that people built to build it. Yeah. it's a lot of tooling. Yeah.
Yeah. So that was very loud. So you just mentioned that you didn't fully understand the heap exploit, but I'm curious if you've looked at this is all in the messages blast store process, right?
Correct.
So do you have any, I guess, opinions or feedback on, do you think the fact that this process that exists only to parse messages or whatever provides an easier target for doing a heap, like heap room or something like that, since it only has one purpose and it spins up only for that?
Right, and one of the things you see here, and it's an open question as to why do they keep crashing it?
So there is a thing which I mean, I'm sure is that like if you actually do start crashing the process, it'll move the shared cache or something like that specifically for.
Right,
Webp.
right.
Do you think that triggered?
Possibly.
Okay.
Possibly. I mean, there are some other kind of fun trivia around messages blast store, in that. So one of my approaches to try to figure this out was, well, you can actually inside your own app. You can call into the passkit APIs to display like these wallet PK pass things. But the funny thing is, if you actually try in your app to render the exploit PK pass, it immediately fails and be like, no, this is a malformed PK pass file, because it is malformed. It's missing like a bunch of required files, and the real parser bails out super early, like well before it parses the Webp. But the messages blast door one, that's the one that's meant to like take untrusted ones from random people on the internet, has a way more permissive parser that's like, oh yeah, give me all those images, I'll just parse them and try them. Yeah. Oh, yeah. Yeah. All right. Thanks, everyone.